Uh, okay, so what I told you yesterday. So I said several words on the interest rate models, products, market. So why it is so important in my personal view? So there are three reasons. So one, interest rates dominate the financial market. So definitely it's the major part exchange, foreign currency products, equities are of course important, but market exposure is much slower. The second reason is probably, I don't know, okay, working in London City or Wall Street had a specific flavor. So this is a region of the world where grit is good, but not discussing if grit is good or bad. We must also think about not only making money, but running the world functioning. And interest rates derivatives are not only linked to people who would like to invest and make money, but as well to everyday functions of banks, which whose function is not only making some people rich, but as well making the economy exist. So, so from the social point of view, interest rate derivatives are important. And the third reason, so probably it's my personal, they are somehow orthogonal to Black and Scholes paradigm. So they fit into very deep philosophy of martingale pricing, but that stops at the end. The, all the models are not descendants of Black and Scholes model, but were creating, so having the concept deeply in mind, but we had to invent something else. So a wheel somehow reproduces functions of a leg, but is not similar. Looks completely differently. So namely, the most important framework. So what's the difference? In equities and exchange and foreign currencies, we've got only one price which moves up and down. Yes, that's the stock price or exchange rate of the currency or something. Here we have whole composite structure of term structure of interest rates which moves. So this is a movement in infinite dimensional space. Of course, we discretize everything because our computers are not smart enough to calculate in infinite dimensions. But in our brains, we think about it as movement in larger functional spaces. So that was probably the conceptual problem of developing the whole interest rate theory. So I've told you somehow in opposite to what I've just said, that interest rate theory is not a descendant of Black-Scholes. I've developed the forward measure paradigm. So that was, in my opinion, that was created by Nicole El-Karoui. In general approach with Frochet and some Elliot Germain, perhaps. Okay, Nicole El-Karoui and her collaborators in the early 90s as change of numeral. So this numeral is a French word which was adapted in English. So that was that important. And then especially developed by Gatarek-Musiela for interest rate products, more or less the same time. And what is, speaking in rough, very rough, so probably I should that formula expose a bit more, is that Xi is contingent claim. Pricing of contingent claims is finding expected values of discounted, so multiplied by discount factors, intrinsic values of these contingent claims. And changing the measure to a special measure called forward measure, which is, say, interest rate oriented change of numeral trick, we may the discounting extract from the expectation and just get this is just discount factor as currently is. So zero coupon bond price. The obligation to pay €1 at maturity capital T. Yes, so at capital T, we get expected value of this contingent claim. And after this a bit lengthy introduction, let me speak about probably the most important model for interest rates, called Heath-Jarrow-Morton model. Maybe I should not use the word model. It is a framework. So this, what we assume, we don't assume much. So we assume that bond prices are differentiable. And this F is just logarithmic because, of course, bond prices must be positive. Interest rates don't have to, but bond prices are always. So this F is logarithmic derivative of the bond price, and this is called usually forward short rate. So finance consists of two components, randomness and future. So this is in rough expectation of the short rate. So expectation at time T, and the short rate will be in the future at time S. So that's the way how we should look at this notion. And then next assumption that forward rates are eta processes. So this is not an assumption practically, so because all the important processes are eta processes. Yes, I know fractional Brownian motion is not, but this is just an assumption. It is tractable. So it is continuous. There are no jumps, and it's got stochastic differential. A and sigma are stochastic processes, so there is no assumption about that. So let us remind how terms defined here at the very beginning of our theory are redefined. So discount factors here is just integral of the short rate. So Fs is a short rate in this term. Yes, because this is forward rate, but not forward. Expectation of the short rate at time S, and the future is not future but present, so it's the actual short rate. So this is discounting, and our martingale defined like that is just that. Okay, so then, so what did Heath-Jarrow-Morton do? So I don't know if you bother when you've got.
Sorry, Dariusz, can I interrupt you because you have a question?
Yeah, definitely interrupt me. I'm dreaming of interrupting.
Why are not saying anything about Markov or not for no?
No assumption. This is
okay.
So that's the reason why I doubt where the word model is correct. Maybe it should be framework. But okay, I had a paradigm here on the slide before, so maybe I didn't want to misuse big words. So, but okay, think about Heath-Jarrow-Morton framework. Who's here? Right. Okay. So believe me, these formulae are correct. And then we've got a fundamental Heath-Jarrow, maybe a comment of this three gentlemen. So Andrew Morton was the PhD candidate. David Heath, who passed away a couple of years ago, was his supervisor, and Robert Jarrow, his referee. So that's the question, who did that model? Okay, I've got a supposition, but I won't state it openly. So, okay, this paper's got 3 authors. And that is the fundamental theory of interest rate derivatives pricing. So the market is arbitrage free. So that means, remind you definition here, market is arbitrage free if that term is a positive continuous marking day, if and only if the drift term in the eta differential here has got that strange formula. So this is drift equals diffusion term, volatility, times integral of the volatility, but not over time, but over space. And these two terms are called forward rate volatility and bond volatility. So bond volatility is capital sigma. Yes, and proof is elementary. So everything consists of eta formulas. So that's the main tool in this business. So just recalculate the eta differential of the process M. Yes, because we've got those definitions. M is so defined, so we calculate its eta differential. So this is, believe me, it was published, so there are no errors here. This is that term. So here we've got dt, the drift term, here, and diffusion. And a process, eta process is a martingale if and only if the drift term is null. So, okay, we must set that term is equal that term. Then we differentiate with respect to capital T, and we get this term. But when you browse the Heath-Jarrow-Morton paper, you won't find it that easy. You know, when you write a research paper, you don't see the hard kernel of the results. So they write about market price of risk, what is in derivatives pricing irrelevant, because the concept of derivatives pricing in general is to be independent on the preferences of agents. So that Mr. Market prices everything for everybody the same way. So, and people may trade. So the law of one price. Of course, there are discrepancies in practice of this law, but they are not big enough to make arbitrage pricing not possible. Okay, so that's very crucial element, and it is fundamental for the general concept of arbitrage pricing, because when we look at the dynamics of forward trades, we see they depend only on one model parameter, which is sigma. A is determined by sigma. So we've got exactly the same situation as it was in the Black and Scholes theory. Because as you probably know, some other guys did try to give option pricing formulae, and they were quite close to Black and Scholes with one difference. Maybe it's good to ask a question to the audience. So will anyone try to answer? What was the biggest achievement of Black and Scholes? Should I ask? I've got your names, so should I ask by person? Good idea. Question to Anna Merkel. What's your opinion about it? Nobody? Okay, I have to answer that. Because in all the previous option pricing formula, there were more unobservable parameters. So in the Sprinkle model, you had a drift term. So it was exactly the same as Black and Scholes formula, but R, short rate, was replaced by the drift term. So he didn't price in the arbitrage free measure. Arbitrage free measure, but in the real world measure. And the drift term for stocks or exchange rates is murky. We don't know. If we knew drift of stocks, making money would be very easy, yes? So we find the stock with the highest drift rate, and we just invest some money in that, shorting the one with the lowest growth rate. Yes, and that's not consistent with the neutral market assumptions, that there are no free lunches. If we make money, we must pay for that with risk, at least. And here, we've got exactly the same situation. The only parameter driving the market is the volatility. Of course, this is a function because we move in infinite dimensional space. So volatility should be a function, but still there is one. There is nothing like drift. So historically, it was not like that. So the Heath-Jarrow-Morton model was created in There was a story in the end of the 80s, but it took several years to publish it. It was not that easy. They wanted to sell this result to some banks, didn't succeed. So there was a story. It lasted several years and it was distributed in preprints. So the community knew the paper before it was published. So it's exactly the same story as with Black and Scholl's paper. So historically, first interest rate models were so-called short rate models. What a short rate consists of. So since M, so that's probably the most important, so discounted bond prices are martingales, then bond price, so this is just mimicking with the martingale property. That property holds that bond price is expected value of the exponents of the integral over short rates. It's a general result. It holds in the every arbitrage-free model. It's not a property of the given model. So then, if we assume that R equal F as namely the short rate, the current short rate, is a Markov process. So as I've told you, all calculations of expected values, okay, let's say practically all calculations of expected value in stochastic processes have somewhere Markov processes as assumption, because Feynman-Katz formula is the fundamental tool of calculated expected values. So relation one-to-one between functionals of stochastic processes and partial differential equations. Okay, so if we assume that this process is a single-dimensional Markov process, so namely it follows the following Ito formula, so traditionally Ito equation that you know probably from your courses in stochastic processes. So by the Feynman-Katz formula, there exists a deterministic functions. We don't know term for this function, which is a function of current T, capital T, and the short rate, that the forward bond price is just a deterministic function of the short rate. So bond price, if we know the price of all bonds, we know, of course, all the zero coupon bonds, of the swap rates, forward Libor rates, and so on, because as I told you in the beginning, the zero coupon bond price is a building block for all financial quantities. Okay, so that's the general result, not very deep one. And particular example. So first one is when the short rate is just an Einstein-Muhlenberg process. So A is a so-called mean reversion parameter. B is important, and I would like you to guess what's the function of that. Sigma is deterministic, so the diffusion term is just Gaussian. And then next question to the audience who hates to answer. Probably you don't listen. What's the function of B? Someone I know, definitely this is a question for David Garcia, if he's there. David, are you there? No. Okay, for someone else.
David uses to arrive late because
of his duties.
The job.
Yeah, okay, so
I will tell him when he arrives.
No, but that I won't wait for him with that question. So the question is to the rest of the audience. Why B? Guess. Wrong questions are wrong answer are good answers. You know that Thomas Alva Edison said that when he spoiled something once again, so he used to say that's not a negative result. I know already the way that should not be done. Did anyone try to answer?
There are some answers in the chat.
Yeah, so please read.
Long run mean value, this is one answer.
Yeah.
Long run interest rate level, second answer.
Yeah.
Curve, third answer.
Yes, all the answers are correct. So why is B? Because we've got that formula here, yes? When we put 0 here, so at current time, we get a formula. Yes, so on the right hand, we've got the theoretical value of the bond. But on the left hand, we know what the value of the bond is. The bond is priced by the market. So those values may coincide, but there is no a priori reason why they should coincide. But if we put here B, so by some simple algebra, we may prove that this B, mimicking with this B, we may fit the current bond price. So make the model consistent with the current market conditions. And that procedure is in numerical methods is separated from fitting the model to the option prices. So first we fit the B to the initial yield curve, and then we fit sigma to option prices. So that is it was a critique of the approach with the short trade, because you see here, yes, the short trade follows a dynamics. It is correct or not, so we've got some reasons why it should be or it should not be. Okay, let's keep that discussion. But B is a function of the current bond price on one hand, but on the other hand, it is a model parameter. So dynamics of a financial quantity should not depend on current market conditions. Yes, so it's counterintuitive, because dynamics should be independent of what we have now. We've got some market states, and the financial the yield curve will evolve the way it evolves. Market conditions should not impose, current market conditions impose the initial starting point. Okay, I agree, but they don't impose dynamics, the drift term for the short trades. And in this approach, it is so. So this is first model. This is Vasicek, Hull-White. So Oldřich Vasicek didn't introduce, because okay, it was first attempt to model interest rates. So he didn't introduce the fitting initial yield curve, the term B. So it was the contribution on of John Hull and Alan White. So when this is called Hull-White model. So, and there is another Hull-White model for stochastic volatility, yes? So maybe we should distinguish them. Okay, so this is a Gaussian model. Next model, here called Cox-Ingersoll-Ross, is where we don't have here just Gaussian noise, but in the diffusion term, there's a square root of the short rate. The drift term is exactly the same with the same problem of fitting initial yield curve. Question to the audience: why, in theory, is the Cox-Ingersoll-Ross model better than Hull and White? Okay, why it was better 10 years ago? Audience, please reply. Replies?
R positive. This is
yes,
answer in the chat.
Exactly. So I've got always very satisfactory answers. So I don't know why you're afraid. So
is
that's
another one not allowing negative interest rates.
Yeah, that's gives positive interest rates. So it was a time period when we expected that interest rates should be positive. So it was 15 years back. Now we know that's not necessary. But the argument that why interest rates should be positive was easy. So if rates are negative, so I take all my money from the bank and deposit, I don't know, somewhere. Okay, I've got many places at home, but that argument is just not true, because having a chest of gold in my garden somewhere, that's dangerous, that costs. So if I deposit a chest of gold in a bank, I will have to pay for that. So that looks like negative interest rates, and rates, of course, may be negative because they are negative, and that's all. There is a magic word already used in another context for this, for another model. This is Bessel, the word. It is a Bessel process, which describes movement of square of a linear process in various dimensions, and they may be partial as well. So it's very interesting theory of Bessel processes, a lot of calculations. And the third most popular model was Black-Karasiński. I've recently found several lectures and articles by Piotr on history of Black-Karasiński model. So he's writing what happened some 30 years back. So that means he's getting older. Yes, that means old people do that way. Since he's older than me, 3 or 4 years, so okay, I don't feel like writing memories still. So that's the reason of development of Black-Karasiński model was the same for Coxinger's or Ross, to grant positive rates. And at the very beginning, these two models were considered better than the short Black-Karasiński model, because we had closed formulae for the function h, the function linking short rate with zero coupon bond price. For Gaussian models, because for Gaussian models we've got, they are known for the last almost 200 years, and during the whole 19th century people did work on deriving functionals of Gaussian distributions. We've got the same for Bessel processes. So this is big contribution of Markovian and other guys who did very sophisticated calculations. For Black-Karasiński, for a long time, we didn't have closed formulae for zero coupon bond prices. But now we've got very efficient approximate formula. And to be honest, we've got efficient approximate formulas for practically all short rate models. So we may invent anything for various reasons. But there is still that but with the B, that stochastic parameter movement is determined by the current market conditions. So it's logically questionable, and you may probably guess how did practitioners deal with that problem. Did you guess? I think I've encouraged the audience to give an answer. So how did practitioners deal with the problem that current market conditions have too much impact on the future dynamics? Joseph, did anyone answer? No. So my answer, but maybe no answer was a good answer. They didn't bother. Because, you know, I will speak at the end of the course about it, but practitioners, they don't care too much about logical consistency. If they've got a formula to price something, they are happy with that. I think it's the proper time to make a short break. Yes, 10 minutes. Okay. Let's move to the applications. So after that violent critique of short rate models, which are still in use in industry, less and less, because, you know, there is some progress in research and in implementations, but tradition is important as well. So let us move to the Heath-Jarrow-Morton model. So how it is, it may be applied, because so far I've presented you the general framework of Heath-Jarrow-Morton. So the main interest rate options are swaptions, caps and floors. So they are so-called vanilla, so the most popular product. So they are based on the consecutive grid. So discretizing of time, and the time from t of the length delta, okay, let us assume it is equal for all the grid points. In practice it is not, but it's not much relevant. The rate prevailing from ti to ti plus 1 is the major underlying, or anything we may build on that. So swap rates, single period rates is the like zero coupon bonds for the linear market. This is the main building block of the volatility products, volatility exposed product. So, okay, define such consecutive points. And again, based on that, forward LIBOR rates defined that way, that forward LIBOR rate are multiplied by the, so annual, it's called annualized, multiplied by the its length +1, or the discounting period, or maybe compounding period, is just B, so zero coupon price at time t minus 1 over zero coupon bond price over t n. And we just take eta formula and derive a not much sophisticated formula for the compound rate, which is a linear function of the LIBOR rate. So believe me, this is correct formula. So the function is not much sophisticated. And I remind you that sigma is, capital sigma is integral of small sigma over space, or space. Okay, and then you will get the simplest derivation of BGM model. So also called LIBOR market model, but because LIBOR is now a forbidden word, it will die out in 6 months. So back to the names of the inventors. Okay, so the dynamics of the LIBOR rate defined by this formula, since LIBOR is a linear function of the compound rate, is just that term. So it's plain algebra. And now we said that this guy here, starting from here, so that what is multiplied by the drift and diffusion term is a linear function for LIBOR. So still we don't make any assumptions. So this is mimicking with formulas. And of course, in that situation, we've got such an equation for the forward LIBOR. So sigma is a bond volatility, is a term here. And taking into consideration this equation, we've got such a formula for sigma. We need some initial condition for that. So I do the simplest assumption, so set it equals 0. And that has a very deep impact on thinking on rates, which I understood, say, quite recently during that Libor conundrum. So, how interest rates were created in the market during the last, say, 30 years. So, borrowing money between banks was quite liquid. So to borrow 1 million for 1 day term, 2 days, 1 week, 1 month, half a year, the prices of money in time were reliable. But after the crisis, the only relatively liquid borrowing and lending between banks was overnight. And to borrow money for 3 months from bank to bank, all have very big rating, AAA or AA. It was not that easy. So that made the Libor less liquid, Libor quotation less reliable, all that problems, legal problems of Libor fixing and so on. And these days, the market participants and regulators think of reducing to only very short rate borrowing for 1 day only. And the 3 months or 6 months Libors will be quoted only as swaps. So there will be a second market collateralized for longer term rates. Not as it was before. Okay, that's a couple of years ago. And that's the reason why Fabio Mercurio modified the Libor market model to consider that. So the modification is very slight, to consider that lending money for longer terms is not that reliable. Okay, so now, having this formula, Libor market model, let us assume that volatilities gamma, so Libor volatilities, are deterministic functions. So if we make this assumption saying that these functions are relatively smooth, or at least continuous, we may use standard fixed point and Picard method to prove there exists a unique solution to the Libor equation. By steps, it may be found in my paper, but just I would advise everybody to make an exercise. Say simple simple exercise from differential equations. And you've heard probably that what I was speaking so much about Markov representations and Markov potential theory, link between stochastic processes and partial differential equations. So the downside, maybe the biggest one, of the Libor market model is that there exists no lower dimensional representation of, sorry, I should forget the word Libor, call it BGM model. Between the BGM model and so there is no lower dimensional representation of the BGM model. We cannot squeeze the model to dynamics of 2 or 3 dimensional Markov processes. For pricing of some products, for instance, American products that may be paid for, callable products. Okay, so you've got the simplest BGM model derivation. But of course, why this model became so popular? Because there was a discussion of consistency of mathematical finance. On the one hand, you had a Black and Scholes formalism, which was applied practically to everything. So it was a convention that volatility represents the option price. So traders started to think in terms of volatility. So of course they quoted interest rate options in terms of Black and Scholes volatility. But on the other hand, the Heath-Jarrow-Morton framework here is not much consistent with Black and Scholes. And there was a question: is pricing of interest rate options using Black and Scholes formula mathematically consistent or not? And in our paper, we've given so people thought it is not consistent, some people, and in our paper, we've given a positive answer. Yes, it is consistent. Why? So, pricing of European interest rate derivatives consists of finding the following expected value. So this is Libor rate set in advance, but settled in arrears. What does it mean? The Libor rate is already known at time Tn-1, but settled at time Tn. So this is a rate from Tn-1 to Tn. So discounting goes up to Tn. But it is known a bit in advance. Now it is with the new rates, it is not like that. It will be known at time Tn. So this is the modification by Fabio. And Andrei Lyasov. Okay, irrelevant. So we've got that expectation, where K is the strike price. So, and now we are making use of the theory which was here, that we may get rid of the discounting of the forward measure paradigm we extract discounting out of the expectation. But under the forward measure, the labor market model is just a geometric Brownian motion, yes? Because here we've got a linear function. Gamma is deterministic. So this is an exponential of a Gaussian variable. And of course, for exponentials of Gaussian variables, we've got closed form formulae, namely this formula is called Black 76 formula, and it was exactly the formula that traders used to price interest rate derivatives. Why black? What happened to Scholz? Why did he change into 76? Next question to the audience. Why not black and Scholz formula, but black 76? Nobody. Okay, I've got the answer. So, okay, there is? No. Okay, so the answer will be mine. Look at that equations, dynamics of the forward LIBOR. There is no volatility, no short rate, and no dividend. So if you have in your memory the Black and Scholz equation, drift term consisted of short rate minus dividend rate. So that means that short rate and dividend rate are equal. So that's a bit funny, yes, because we don't see any dividends in the interest rate market, but here in the model we've got dividends and they are equal short rate. And that was a paper written by Fisher-Black in 76 that this is the proper way to price forward and future contracts. So we just take the dividend rate equal short rate. So here in the formula it is. So, okay, very fine. Pricing couplets and floorlets is consistent with the market practice. So it was an achievement, but I didn't know then. It was one of many papers I used to write, but Marek and Alan knew that value of that. Okay. And now, so the part of my lecture dealing with equity and currency options dealt mostly with the problem of existence of smile. Yes, we had it was the big critique of Black and Scholes formula, because things that we expect to be Gaussians are not Gaussians. There is that that picture on the implied volatility and what to do with that. And of course, there were several solutions. So namely stochastic volatility, local volatility, stochastic local volatility, various models, and so on. And of course, in the interest rate world, the situation is identical, because the life doesn't want to follow theories. So what we do with interest rates to fit to the volatility smile. So the answer was already given, exactly the same as we do in equities and FX world. So first, we may introduce, here we've got deterministic gamma linear function L, and we've got Black and Scholes formula. If we replace it by a general stochastic process, we'll get other prices. So the question is, what general stochastic process? Of course, gamma may be a stochastic process. And L, we may introduce constant elasticity of variance or displacement. And we will get some option prices which will be consistent with the market quotes or not. So the displacement here works quite good and is popular in practice because of the Black 76 framework. So the drift term here doesn't exist, is null. So we may easily get close for formulae for option prices.
And there is a question on the chat that maybe would be answered. It says, so can we say your models look like a series of black models for each Ln, as long as we deal with Keplets?
Yes, but yes. So the exact answer is yes, and a bit approximate answer is we may extend it to swaptions. I will speak about it. And I think it's the major upside of the model, so that it is quite convenient for swaptions. Because couplets are not that important, so it's a minor part of the market. The major part are swaptions, of course. and of theory. Next slide will be about swaptions. But let me finish that the stochastic volatility, normally we assume independency of W. Anyone's got an idea why? No correlation of between gamma and W. Why? Because in the equity, what you can deal with correlation. Try to answer, guys. We should be taught neurology because listening activates only a part of our brain. But when we reply, it activates another part. So you think better when you participate in the lecture. You learn more. So it's easier to remember when you ask questions or give answers. So it's proven. So, okay, the answer is here. Here. Because in the FX equity world, we only deal with one measure. So there are two measures, real world measure, which is irrelevant, and risk neutral measure, which is important. And this is the only measure. So under this measure, we may handle one or another way correlation. But here, we mimic with various measures. So interest rate pricing is a nice measure algebra. So I think that's a real contribution of finance to mathematics, that we create some algebras of measures. So of course, Girsanov did it, say, some 8 years back about it, but he didn't make it operational. He's just proven his theorem. And here, the measure algebra is operational. We move from one measure to another by some Girsanov exponents and have fun. Okay, so that's let us move to swaptions, which are.
There is another question.
Yes.
Can you explain the limits in the sum or in sigma? I suppose it refers to the previous slide. Can you explain the limits in the sum in sigma?
Yes. Yes, so that here, this term is just moving with sigma t tn to the left-hand side, and the rest to the right-hand side, we get a sequential formula, recursive formula, yes? So this recursion, of course, is to be solved. And this will be sum of such terms. But we need an initial condition for a sum. Yes, it must be something for sigma t0, this term. And I assume it is simplest possible solution. Equals 0. And what does it mean in financial terms? It means that Libor quoting is reliable. So 3 months, 6 months Libor is just. It's the notion that is quoted by the market. And Mercurio and Liasov skipped that assumption because it is not more reliable. But okay, the theory is valid if I take this this formula. So everything works perfectly. I've got prices for everything, but I've got a silent assumptions that we may believe in LIBOR. I didn't know it for many years, what it means, but you know, it's finance that is so funny that mathematical notions are represented by financial reality. Okay. Swaptions. So the swaption rate is defined as follows. So on one leg, we've got floaters. So bonds paying LIBOR rate at every coupon date. Yes, coupon date is TI, and at this coupon date we got LIBOR, and fixed leg pays at every coupon date a fixed number called the swap rate. So to make these two bonds of equal value, we must of course write down such an equation that here we've got the value of the floating leg, here fixed leg, and it should be equal. So S and N of T should be equal that time. And doing some algebra, we've got that value. And this multiple discounting, which was probably the ugliest part of my presentation, which may be removed from the expectation, and we may create forward rates associated to multiple discounting, not a single. So is defined here. So this is this sum of discounting to various coupon rates. So the Girsanov exponent is defined that way. So I'm repeating the theory of yesterday, and the measure is defined that way. Okay, and then the new winner process got that ugly form. And again, for the swap rate, we apply the Ito formula. So the dynamics of the swap rate follows. That term, but on the other hand, this is just Ito formula. So derivative, first derivative of S with respect to LIBOR of swap rate with respect to Libor times Libor, blah, blah, blah. But keep in mind here, it's not as perfect situation as for the couplet, because gamma is no more deterministic. Yes? So that dynamics is all right, but we won't have the nice log normal properties. But okay, this term is a bit lengthy, so you don't have to remember it, but I think so. But you should know what it represents. So there are logarithmic derivatives of the swap rate with respect to Libor. So I had to calculate it, and work within a band consists quite often of calculations, agree formula. So believe me, it is true. It was tested. But what's the function of Q? Q so gamma NN and gamma K, which is deterministic, remind you, are linked mutually by this formula. Yes, here is gamma, so this is the swaption dynamics. Gamma K represents the forward Libor dynamics. And the so linked by the linearly linked. And I make an ugly assumption from mathematical point of view, but from practical point of view, quite useful. This is called freezing at maturity. So I replace stochastic processes, which actually Q's are, by a deterministic component. And what I get, of course, this is an approximation. I've got a relation between model parameters, namely Libor volatilities, with swaption volatility. And with that approximation, okay, how accurate is that approximation? It was proven it is quite accurate. There are better approximations, but probably I shouldn't bother you with that. And by the forward Libor paradigm, swaption price is equal to that. So if we put these approximations into this expectation, we get again swaption Black 76 formula. Yes. And that's probably the main practical use of the BGM model, because it gives us building blocks here to price swaptions. Okay, so what's next? So let me believe it is relatively accurate.
Oh, there is
Yeah,
a question. A question, yes. The question is swap rate far off log normal?
It is not. So this approximation is accurate, and there is another log normal approximations with such, okay, you see my hands are far away, with such length of formulas, which is perfect. So, and there was some theoretical investigation. So this is practically log normal. So not log normal in mathematics, log normal in finance. Okay, so what we will do. I remind you how the quant works. So we've got the word which gives us prices. We've got prices of instruments that we trust. So in practice, these are European plain vanilla options, put and call. And on these prices, we built a model which fits more or less the liquid prices, and then use with that model many other things. So calculate sensitivities, price less liquid instruments, report risk to the management. But the first step, so where we go from the market to the theory, is called calibration. Okay, so what about calibrations of swaptions? Make such definitions which are, say, pieces of correlations. Now, covariances. Covariances are more important than volatilities. And the sigma square, this one, which is responsible for the black 76 volatility, is more or less equal that term. So under the assumption of freezing, previous one. And if we agree that this freezing method is sufficient, calibration of the model consists, Q's are known, so consists of finding these terms of phi IL of J. So these are functions of the discrete parameters. And we've got a very interesting equation down here, because we've got n times n plus 1 n plus 2 over 6 parameters, but only n times plus 1 over 2 swaptions, quoted swaptions. Yes, because swaptions are quoted on half of a matrix, and these model parameters are half of a cube, more or less. Would anyone comment that? Is David here?
Dariusz, I talked with David some minutes ago. David is from meeting to another meeting.
Yeah, I know that life.
Yes, you know.
I know that life. Anyone else?
he has not been able to connect this morning.
Anyone else to comment this inequality? What's upsides and downsides? And I think you won't find any answers in books. It must be in your mind. So that's any comment? I'll give you several seconds. Okay, it's question time. So this is my first question. So that inequality is good on one hand and bad on the other, because when we've got many model parameters and less market observables, we may expect, we may get a perfect or good fit, yes? Because if we had, say, only n parameters and n+1 observables, so it's difficult to, with 3 parameters, to fit to 6 parameters from the market. And prices, market prices, rarely listen to theory. So when we say we've got a perfect theory, it should be like that. So the prices, the very next day, start to appear beyond your area. So that's a general rule. Murphy's rule, probably. So if we've got many parameters, it is probable that we find a perfect fitting. But on the other hand, there is a danger of overfitting, of fitting a non-intuitive way, of using too many parameters that will not be understood by traders. And the quant role, okay, there's many roles of quants, but one of them is to create the language for traders, the way of speaking on prices. And because if you describe something, you've got at least a part of control over that. So we must use imagination and the real reason. So Nicolas Gomez-Davila used to say that mathematics is a substitute for reason, that it's an artificial leg. So you may walk, but you cannot run. Okay. So to start trade now, probably it's another very important model. So I will need at least 30 minutes to describe it completely. So that will be the last part of the interest rate session tomorrow. So I will speak in the first hour of the lecture, and the second we will start with credit risk. So, and now please ask questions because we've got still 5 minutes. But if you ask questions, I will stay as long as I can.
Okay, 5 minutes for questions. There is a question in the chat. I read. For calibrations, since couplets depend on volatility, can we use them as well?
Yeah, yes. So couplets and swaptions are separated to some extent, but mostly linked. So I use couplets to calibrate the model, couplets and swaptions. So I say couplet is a degenerate swaption.